Hello. Today I'm going to talk about Wien's law, which comes in the context of the early days of quantum mechanics. So this is the Planck curve for a black body radiation. Actually, this is what comes from the experimental data for a black body of a given temperature T. For higher wavelengths, you have low energy, then the energy or the energy density in this case increases. For a given lambda, which we'll call lambda max, there is a maximum of emission. And then for lower wavelengths, it decreases again. So this is the experimental curve. Planck came up with this explanation using the quantization argument, and he came up with this function that describes this curve. Okay, even before Planck did this approach to fit this curve using the quanta as an argument, Wien came up with this relationship between the lambda of maximum emission and the temperature of the body. They are inversely proportional and equal to a constant, which today nowadays we call Wien's constant. So in many textbooks they tell you, well, you should derive this function and equal this to 0, and then you will find Wien's law. Okay, but why is that? Well, if we take a look at the slope of this curve on this range here, it is a positive slope. Then when you come to this to exactly this point, the slope is 0, and then you have a negative slope for these larger or higher wavelengths. Okay, so the slope is 0 here, and if we derive this function and equal the result to 0, then of course we will find a relationship between lambda and t, and I'll show you how we can actually do it and what are the difficulties in doing this. Okay, so this is the goal of this video, is to obtain Wien's law using Planck's function. Just remember that historically Wien came up with this relationship without knowing this function. Okay, so he knew about the experimental data, but he didn't know about the function that Planck came up with. So, but if both approaches are consistent, then we should be able to derive this function and arrive or find and derive Wien's law. Okay, so in order to do that, I'm going to rewrite this energy density function in a slightly different way using constants. So 8 pi ch I'm going to call C1, and then hc over kt I'm going to call C2. And if I do it and substitute it here, I'll have moving lambda upstairs, so that's why we have the negative sign here. And then here I did the same thing, so it's C2 moving lambda to the upstairs. Then that's why we have a negative, and then negative sign here, and then moving the whole denominator to the to the upstairs position right here, and then that's why we have a -1 again. So this will hopefully help us to derive this function. Remember, we have a product of two functions. You can think of this function as a product of two functions, which in turn are a function of lambda. You have lambda here and lambda here, and these two functions are multiplied by one another. So for those who are familiar with calculus, we right away know that we have to apply the product rule of derivatives. Okay, so that's what we'll do. We'll apply the product rule. It tells us that you should derive the first function, multiply by the second, and then add the result to the derivative of the second one multiplied by the first one. Okay, so let's do this. When I derive this first function, I come up with 5 minus 5, actually minus 5 C1 lambda to the -6, just a standard derivation. You just apply the basic rule of derivatives here, and then you multiply your result by the whole of the second function, which is right here, and then you have to add this result to the first function multiplied by the derivative of the second. So I will add, but it will soon be clear why we have a minus sign here. So I'm going to add the first function, which is here, to the derivative of the second function. So when we derive the second function, it's minus 1, that's the minus sign here, and this whole thing becomes to the minus 2, which is here. But remember, we are deriving with respect to lambda, so lambda is inside the parentheses here, so we have to derive whatever function is inside the parentheses, and then we have two functions inside the parentheses, the function, the exponential function, and the minus 1, which is a constant. So we have to calculate the derivative of this function, and the derivative of the exponential function is just the exponential function itself. But then again, lambda is in the argument of the exponential function, so we have to derive lambda. So, and if we apply the derivative rules, derivation rules here, minus c2 lambda to the minus 2. So we apply the product rule, but when we came to the derivative of the second function, we had to apply the chain rule. So this is a very nice example of derivation because of a derivative, because you have a the chain rule inside the product rule, and sometimes that's what you get. But if you do it carefully and you pause the video and you try to do it by yourself, just remember you have a product of two functions, then you apply the product rule, but then when you come to the derivation of this the derivative of the second function, then you have to apply the chain rule. So it's the derivative with respect to the minus 1, then you have to derive whatever inside is in the parentheses, and then you have to derive the argument of the exponential function, and everything equals to 0. Okay, so I just copy this and I put this guy to the other side. Okay, so starting here to the other side of the equation. So but remember, you have a c minus c1 and a minus c2, it becomes a plus sign. But then when it gets to the other side, it becomes a minus again. So it's minus c1 lambda to the minus 5, this guy here, this guy right here, and this guy right here without the sign because we dealt with the sign before. Okay, so we can simplify the c1, we can simplify this negative sign, we can actually simplify the exponent of this function because this is the same function right here, and if we do it carefully, we will get to this point, okay, which is minus 5 lambda e to the c2 lambda to minus 1 plus 1 equals these surviving functions on the other side. But remember, c2 equals hc over kt. We said that in the beginning, so I will substitute back c2 on the function that on the equation that we found, and by doing that, that's what I get. Okay, but then I can transfer this lambda to the other side and call hc over lambda kt. Remember, because I have hc lambda kt here, hc lambda kt here, and then here. Okay, so I can just call this x, because this x actually has the two variables that I'm interested, lambda and t. Okay, so I have to solve this equation for x. This is the result I get, and then I can just apply the distributive property here, and I arrive at this function. And then if I simplify a little bit further and multiply by minus 1, I get this function. Okay, so this function is e to the x multiplied by x minus 5 plus 5 equals 0. If I can find the solution for this function, I can find the value of x, and if I substitute the value of x here, I can arrive at a relationship between lambda and t, since h is the Planck's constant, c velocity of light, and k is Boltzmann constant, which are known constants. Okay, so I'll just have to find the value of x that satisfies this equation. But I will leave it to the second part of this video to show you that this equation is not so easy to solve. Okay, so in the next part we will use Newton's method to find a solution for this function and eventually arrive at Wien's law. Okay, I hope you enjoyed the video so far. If I had made any mistakes, or if you have any comments, please leave your comments below, and I'll see you on the continuation of this video. Bye bye.